All right. Good morning, everybody. Welcome to yet another virtual session. We have a lot of material to cover today. Are you able to hear me okay?
Yes.
Awesome. Before we get started, where is the professor in class? Has he finished electrochemistry? Has the professor finished chapter 17 on Tuesday? 17 being electrochemistry, okay. So he hasn't started nuclear chemistry, is that right? Have you seen stuff like alpha particles? Good. Thank you. Okay, so that leaves us with plenty of time to go over electrochemistry today. And I think in the remaining time, we can also talk a little bit about nuclear chemistry. All right, let's get started. Yeah, grading is still based on attendance. Oh, every time you attend the Zoom meetings, the your attendance gets recorded, so I can go back and look at it. Yeah, only when it's in person do I need to take physical attendance. If it's through Zoom, then it's automatically getting taken. Okay, all right. Did everybody, just as a reminder, I sent out a thermodynamics recorded lecture. Hope everyone saw that. That should have covered everything that was in that chapter. But okay, let's get started. Electrochem. First thing in electrochem is determining unknown charges. You've already seen this before, but here's a quick recap. Suppose you have an ion that looks like this, Cr2O7 2-. Okay. Usually, generally speaking, this is what goes on as far as charges are related. If it's a main group element, then you can figure out what its charge is based on its valency. So the magnitude of the charge is just going to be given by its valency, which remember is the small of the group number and minus the group number. Okay. If it's not a main group element, then think of it as an exotic atom. Let's say the charge is going to be unknown. So that is what you'll be solving for. So for example, here in this example, Cr2O7 2-, the chromium is exotic because it's not a main group element. Oxygen, as usual, we've seen oxygen before. It's a main group element with a charge of 2, but negative. It's a nonmetal. So how do we set up the algebra here? We've got 2 chromiums, so 2x plus 7 oxygens, 7 times -2. And the whole thing should come to a charge of a -2, which is the charge of the net charge of the ion. Was there a question? Okay. Yes, like always, feel free to unmute yourself and ask me a question if you have to. All right, so let's solve for x here. 2x minus 14 equals, so 2x equals 14 minus 2, which is 12. And so x equals 6. This is how you determine charges. Another example, figure out the charge on manganese, Mn. Okay, so that would be X. There's two oxygens, each carrying a charge of -2. It's a neutral molecule as a whole. It's a neutral compound. And so the whole thing comes to 0. So X is 4, +4. So manganese here has +4 charge. It's very important that you get this part. Any questions? Okay. We'll see more of this in a little bit. Now let's jump to balancing equations. And a very quick thing before we balance equations is the concept of reduction and oxidation. This chapter is all about electron gain or loss, right? And the way I remember which one's which is I look at reduction and I think reduction involves reduction in charge. And so this guy is going to be a gain in charge. That's all you need to remember. Reduction means reduce. And so oxidation is the funny one, it's gain. Okay, so let's work with balancing redox reactions. Yikes. And here's an example. Cr2O7 2 minus plus E 2 plus gives Cr 3 plus Fe 3 plus. Okay. Here's an unbalanced redox reaction, and the question will always tell you to do it either in acidic medium or basic medium. We'll start by balancing this in acidic medium. To balance it in basic medium requires one last modification all the way at the end. So no matter if it is acidic or basic medium, you're going to do the same, a common series of steps, and then make one last modification at the last step. Okay. So the first thing that you do is you figure out which two atoms are changing charge, right? Since this is a redox reaction, one atom is getting reduced, the other atom is getting oxidized. You just need to figure out which one's which. When you are trying to figure out what two atoms are involved in oxidation and reduction, look at the ones that look exotic, the ones that are non-main group elements. Hydrogen and oxygen are usually pretty boring and are not getting oxidized or reduced. So I'm going to look for anything that is not hydrogen and oxygen. So I'm going to look at these two guys. And already you can see Fe goes from a charge of +2 to +3. So Fe is definitely undergoing a charge change. There to there. Great. So we've isolated one atom that is undergoing a charge change. My hope is that the chromium is the other thing that's undergoing a charge change. So let's check. Here, I know what the chromium's charge is. It's +3 because that charge is only on the chromium. So it's got to be chromium's charge. Here, on the other hand, you have the 2- charge on the whole mess, 2 chromiums and 7 oxygens. So we're going to use algebra to separate out the charge on the chromium. Once again, there's 2 chromiums, so 2x, 7 oxygens, each carrying a charge of -2. because that is oxygen's valency, and oxygen is a nonmetal, so it's -2, for a total of -2 charge overall. And like we've seen, X, when you solve for this, comes out to +6. So chromium is going from a +6 charge to a +3 charge. Great. Now let's separate the two out, right? This is called splitting it into the half reactions. A redox reaction is reduction and oxidation, right? Combined together. So we'll need to peel them apart, separate the reduction and the oxidation. So I'm just going to copy down one of them. Cr072 minus becomes Cr3 plus. And on the other side, I've got Fe2 plus becomes Fe3 plus. Remember, on the left-hand side, the charge, our focus is only chromium, nothing else. Chromium is going from a charge of +6 to +3. And on the right-hand side, iron is going from a charge of +2 to +3. Which one's oxidation, which one's reduction, left or right? You tell me.
Reduction left, oxidation right.
Exactly. This is reduction. Left is reduction because the charge is going down, +6 to +3. So this is the reduction half. And the right-hand side is the oxidation half. Once you've identified the reduction half, which is the easier one, right? Because charge is going down. The other one's got to be the oxidation half. Great. So the idea is you separate them into the two halves and then you balance them separated. And then when each of the halves are balanced, you recombine them at the end. So start with the combined unbalanced, separate, balance, combine. Okay, so how do we do this? You start by balancing out anything, any atom except hydrogen or oxygen. These are special, we'll balance them in special ways at the end. So let's see. I've got 2 chromiums here, 1 chromium here, so I'm going to put a 2 to balance out the chromium. On the right-hand side, iron, 1 on each side, so that's balanced. Next comes in electrons. You need to put the appropriate number of electrons on each side. Now, electrons are negatively charged, right? There's many ways in which you can remember where to put the electrons for reduction. Reduction, because the charge is going down, well, charge goes down because something negative was added. Electrons are negatively charged, so reduction involves a gain in electrons. Which means for reduction, the electrons go on the left-hand side, on the reactant side. Now, all we need to figure out is how many electrons. Now, here's where you'll need to remember something very important. Chromium is undergoing what kind of a change here? +6 to +3. What change is that? As in, how many electrons is chromium gaining, going from +6 to +3?
+6.
Say that again.
+6.
+6. Okay, so you're jumping ahead. Good. But +6 to +3, that's a difference of 3, right? What I want you to remember is that it's 3 electrons per chromium, per single atom of chromium. So you're not going to add +3 electrons on the left-hand side. There's 2 chromiums on each side. So you're going to have to double it before you put it in. Cr2O7, 2 minus, plus 6 electrons gives 2 Cr3 plus. 3 electrons per chromium because 6 minus 3, charge goes from 6 to 3, but there's 2 chromiums on each side, so you double it. The right-hand side is very simple. We have a charge difference of 1, and you're going to put that on the other side, on the product side. In oxidation, electrons are released. Excellent. Next up, you're going to balance the electrons on both sides. On the left-hand side, you have 6 electrons. And so on the right-hand side, you're going to take the whole equation and multiply it by 6. So that gives you 6 Fe2 plus, gives 6 Fe3 plus 6 electrons. Amazing. And then
I have
you're
a
going to
question.
go ahead.
So you see the -2 on the Cr2O7? So we don't take account on that plus the 6 electron.
Exactly. You only look at the charge change on your atom of interest. That's all.
Okay.
That's why we did the algebra.
Thank you.
So you're only looking at the charges on the chromium, nothing else. Great. So now electrons are balanced, 6 electrons on each side. Great. And then you move on to balancing out the remaining hydrogen and oxygens, starting with oxygens. Oxygens first, hydrogens last. You balance oxygens by adding water. You balance hydrogens by adding H plus. Great. Left-hand side, I've got 7 oxygens on the left-hand side, none on the right-hand side. So I'm going to add 7 water molecules, 1 oxygen per water, right? So if you need 7 oxygens, you'd add 7 water molecules. Excellent. There's no oxygen business happening in here for the oxidation half, so I'm going to leave this alone, the green side.
I'm sorry, I think I missed a part. I'm sorry, can you just reiterate why we're adding 6 electrons to chromium?
Oh, you see the charge difference? Chromium goes from +6 to +3.
Yeah.
That's a difference of 3.
Yeah.
But it's for 1 chromium. We've got 2 chromiums on each side. So you double it.
Okay. All right. Thank you.
No problem. On the right-hand side, you don't have any oxygen, so no adding water business. Okay, now let's balance hydrogens. Going back to the red side, I see no hydrogens on the left-hand side, 14 hydrogens, 7 times 2 on the right-hand side. So I'm going to add 14 H pluses on the left-hand side. Once again, no hydrogens on either side of the oxidation half, so the green side remains unchanged. Great. Everything's balanced now. Now you can recombine. Everything on the left remains on the left, everything on the right remains on the right. So Cr2O7, 2 minus, plus 6 electrons, plus 14 H plus. This is all that was on the reactant side of the red. On the green, this is what I had on the reactant side. Cool. Now the product side on the red is 2Cr3 plus 7H2O. And on the green side, you have 6 Fe3 plus and 6 electrons. Fantastic. If you did this correctly, the electrons should cancel out at the end. So let's clean it up. Well, there is nothing to clean up. This is it. If there's anything common on each side, you would cancel it. So for example, if you see a 14H plus here and a 6H plus here, for example, you would cancel the 14 and 6 and make that 8. Right, 14 minus 6. That's just some cleaning up. We'll work with examples where that is involved. Change this back. Great, so that is the final answer in acidic medium. In basic medium, there's one thing that changes. And the one thing that changes is that anytime you see an H plus anywhere on the reaction side or on the product side, it needs to get neutralized because H pluses don't survive in basic solutions. H plus is acid. Acids don't survive in basic solutions. They get neutralized. So the last step to go from acidic to basic medium is to neutralize any H plus with OH minus. H plus OH minus, they react to neutralize each other to form water. Now look, 14H plus, I see an H plus here, so I'm going to add an equivalent amount of OH minuses, 14 OH minuses, and then take them out. Oh, by the way, you have to do the same thing on both sides. This is the only step where you add something to both sides because you're dealing with an already balanced equation. So you add 14H minuses on both sides. And on the left-hand side, you neutralize the H plus and the OH minus to waters. But now I have a water here and a water here. So some cleaning up, 7. That becomes a 7. And so the final version in the basic medium is going to be dichromate ion, CO2O7 minus, plus 7 water molecules, plus 6 Fe2 plus, gives 2 Cr3 plus, plus 6 Fe3 plus, plus 14 OH minus. Any questions? Why is it 6 electrons for the reduction? Was that, honey, do you still have that question or I didn't see it? Okay, why is it 6 electrons for the reduction? Let me see. Where's the reduction side? So you understand why it's 3 electrons per chromium, right? We're going from plus 6 charge to plus 3 charge on the chromium. That's 6 minus 3. That's a difference of 3 electrons. But that's only if you're looking at a single atom of chromium. We've got 2 chromium atoms on each side. See? 2 and 2. So that would be 3 electrons. Sorry, 3 plus 3. So 6. Does that make sense? Yeah. Oh, no. When you're looking at the charge change, you're not looking at the charge on the overall ion. This thing, you no longer care about this. You only care about the charge on the specific atom that undergoes the charge change, which is chromium. So you're only tracking chromium from here on. You're only tracking chromium on the left-hand side, and you're only tracking iron on the right-hand side. The charge on a single atom of chromium and a single atom of iron on each side. Here, it's not that chromium has 6 electrons, it's that chromium is missing 6 electrons, and here chromium is missing 3 electrons. That's a change in missing of electrons of 3. Confusing, I know. But the charge has gone from +6 to +3. That's a 3 difference in charge on chromium. That's all I care about. But per chromium, and there's 2 chromiums, so 3 times 2 is 6 electrons. If you're still confused, let's work with another example so that I can continue to clarify this. I'll actually do 2 more examples because this is pretty important. Balancing redox reaction. I need, okay, great. Here we go. ClO3 minus, okay, great. Here's another example. Balance ClO3, no, just a single minus, plus SO2 gives CSO4 2 minus plus Cl minus. Awesome. Once again, oxygen is boring. And so the only non-oxygen atoms that I see here are chlorine and sulfur. So our initial guess is that the chlorine and the sulfur are undergoing charge change. Cool. So let's start doing our algebra. Let's start with this guy. Chlorine is X, unknown. We have 3 oxygens, each carrying a charge of -2. It should total -1 because that's the overall charge. X minus 6 is -1, and so X is 6 minus 1, 5, plus 5. So chlorine is going from +5. You're not gonna look at this number anymore. You're only gonna focus on this guy because chlorine is what we're interested in, not the overall molecule or ion. Let's do the same game with SO2. Sulfur is X. There's 2 oxygens. It's a neutral thing, so equals 0. X equals +4. Great. I'm only going to look at +4 now. Same thing with sulfate. X plus 4 times -2 for oxygens equals an overall charge of -2. So X minus 8 is -2. X equals +6. All right, that's +6. And then lastly, for chlorine, I don't need to do anything because it's a single chlorine, and I know the charge on that chlorine is -1 because it's alone. If something's alone, you don't have to do any algebra. If it's with other atoms, then you have to do the algebra to isolate the charge on your atom of interest. Cool. So what atom is getting reduced? What atom is getting oxidized? You tell me.
Chlorine's getting reduced.
Chlorine is getting reduced, exactly.
And sulfur is getting oxidized?
Yes, correct. Chlorine is going from +5 to -1. That's a reduction. So that's... And sulfur is going from +4 to +6. That's oxidation. All right, let's separate the 2 halves. ClO3 minus becomes Cl minus, and SO2 becomes SO4 2 minus. Balance all the exotic atoms. Chlorine on the left-hand side balanced. Sulfur on the right-hand side balanced. Great. Put in electrons. We saw for chlorine, the charge goes from +5 to -1. That's a difference of 5 minus -1. It's a difference of 6 electrons. That's a reduction. So 6 electrons are gained. Sulfur, charge goes from +4 to +6. That's a difference of 2. 2 electrons are lost per sulfur. Here, we're not multiplying the 6 electrons and the 2 electrons by anything. We're not doubling or tripling it because we have 1 chlorine on each side and 1 sulfur on each side. If you had more, you'd multiply by the appropriate amount.
Is there like a set thing that like for the reduction, the electron always goes on the reactant, and
Mhm.
then for oxidation, it always goes on the product?
Correct.
Okay, got it.
Mhm. For reduction, the electrons always go on the left-hand side, oxidation always on the right-hand side. Correct. Okay, let's balance out oxygens. 3 electrons here, 3 oxygens on the left-hand side, so I'm going to add 3 water molecules. 2 oxygens here, 4 oxygens here, missing 2 on the left-hand side to 2 water molecules. And then lastly, hydrogens. There's 6 hydrogens here, so I'm going to add 6 H plus on the other side. And 4 hydrogens here, so I'm going to add 4 H plus on this side, the right-hand side. Great, everything is balanced. Let's make the electrons equal. Let's take this side, multiplied by 3, because this has 6 electrons, this has 2. And so that gives you 3 SO2 plus 6 H2O, gives 3 SO4 2 minus, plus 6 electrons, plus 12 H plus. Recombine, ClO3 minus, plus 6 electrons, plus 6 H plus. Right, everything on the left remains on the left, so this and this. Plus 3 SO2 plus 6 H2O gives all the stuff on the right-hand side. Cl minus 3 H2O, 3 sulfates, 6 electrons, and 12 H pluses. If everything went well, the electrons should cancel as they do. 6 H pluses cancels with the 12 H pluses to make this 6 H pluses. 3 water molecules cancels with the 6 water molecules to become 3 water molecules. I'm just canceling out commons on each side. And so the cleaned out version is this plus 3SO2 plus 3H2O gives Cl minus plus 3SO4 plus 6H plus. Great. This is done in acidic medium. Going to basic medium, neutralize any any H pluses. So 6 OH minuses and the same thing on the other side. This becomes 6H2O. The 3H2O cancels with the 6H2O to become 3H2O. And so the final answer is ClO3 minus plus 3SO2 plus 6 OH minus gives Cl minus plus 3SO4, 2 minus plus 3H2O in basic medium. Yeah, So every time I do redox questions, I'll do both acidic and basic medium, just to illustrate. Yeah. Okay, one more example, and we'll speed through this. Let me see if I can find a really complicated looking one. This is nice. Not really. Oh, this is nice. H2S, HNO3. Gives NO plus S plus H2O. Okay. Let's run through this one. Remember, H2Os, you get H2Os as part of balancing stuff, right? Remember, to balance oxygens, we add on H2O. So if you see H2O from the get-go, you don't need it. Take it out. Because you can tack it on at the end when balancing oxygens and hydrogens. Remember, oxygens and hydrogens are boring. You don't have to worry about them initially. I think this is where all the interesting actions happening. So I'm just going to focus on this. If you want, you can keep the water. It doesn't matter. And put that water either in the oxidation half or the reduction half. It will not change a thing. But I feel like this will be easier doing it this way. Cool. So H2S, hydrogen's boring, sulfur is interesting. So 2 times 1 plus X is 0 because it's neutral. So X is -2. Let's do -2. HNO3, hydrogen is boring. 1, nitrogen's interesting. Oxygen's boring. Equals 0. So that's X equals 4 minus 1 plus 3. And O, X plus -2 is 0. X is plus 2. And sulfur is just alone with no charge. So that's a 0 charge. All right. Clearly, sulfur, nitrogen is getting reduced. Oxygen is, sulfur is getting oxidized. And so let's separate these out. HNO3 becomes NO. H2S becomes S. I'm going to rewrite the charges here. It's going from +3 to +2. And this thing's going from -2 to 0. 1 exotic atom on each side, 1 nitrogen on each side, 1 sulfur on each side. So I don't have to worry about doubling or tripling. 1 electron is gained here, 3 minus 2. That's a difference of 1. On the other side, 2 electrons are lost. Okay. Great. Sulfurs are balanced, nitrogens are balanced, electrons are balanced. Let's times this by 2 to make the electrons the same on each side. 2 HNO3 plus 2 electrons gives 2 NO. And then lastly, balance out the oxygens and the hydrogens. So no oxygens here, so I'm just going to add 2H plus. That's good. Here I have 6 oxygens on this side and 2 oxygens on this side. So this needs another 4 oxygens, so 4 H2O. And then lastly, to balance out the hydrogens, this is 8 hydrogens, 2 hydrogens, so plus 6 H pluses. Great. Recombine. 2HNO3 plus 6H plus 2 electrons plus H2S gives 2NO, 4H2O, sulfur, 2 electrons, 2 H pluses. 2 electrons cancel. 2 H pluses, that's 4 H pluses. And that's it. So 2HNO3 plus 4H plus H2S gives 2NO, 4H2O, and S. So this is done in acidic medium. In basic medium, let's make the jump real quick. 4 OH minuses. For H2Os. And so the water molecules cancel on each side. And so you get 2HNO3 plus H2S gives 2NO plus 4OH minus plus sulfur. And this is in basic medium. It's not bad at all. It's just very algorithmic. There's a couple of steps, but at the end of the day, it's very easy. Okay. Any questions? Okay. All right. Let's move on to a slightly different topic, which is by the way, you can also be asked, instead of balancing a redox reaction, just to balance one of the halves. So instead of, for example, instead of being given this whole question, which consists of oxidation and reduction, you could just be asked to balance this guy, 1/2. So basically you would do everything until you get to this point and then stop. There is no recombining, there's nothing like that. Right, so that's the easier question, balancing oxidation half or reduction half. Cool. By the way, figuring out the charge, the unknown charge on an atom, another name for that is figuring out the oxidation number. Same thing for the purposes of this chapter. All right, so the next big topic is cells, batteries. And cells, very roughly speaking, look like this. Cells operate because of a redox reaction. So underpinning any kind of cell in the world is a redox reaction. And the general setup of a cell looks like this. You've got 2 buckets. You stick 2 kinds of metals in them, fill them up with some kind of liquid. If, say, this is metal 1, then the solution has ions of that metal. Let's say this is 2+ charge, pretend. Let's say that the other metal that is M2, and so the solution must have its ions, M2, let's say 3+. Then you connect them through a wire, maybe channel them through a voltmeter so that you're reading what the voltage is. Whoops. Or a light bulb or anything like that. And then to complete the circuit, this is just for electronic purposes, you connect the solution on one side to the solution on the other side via what's called a salt bridge. This is what a cell looks like. 2 tubs, 2 metals stuck into their own ion solutions. Okay. Now, having understood what a general cell looks like, this is so annoying. Okay. There. Now there's two main types of cells. There's the voltaic cell, and then there's the concentration cell. Voltaic cell is if the two metals are not the same. You have two different kinds of metals stuck into two different fluids of their own ions. That's a voltaic cell. If the metals are different. And the idea is two different metals, each metal has a different affinity for electrons. One metal likes electrons more than the other. And so one metal pulls the electrons from one kind of metal to the other kind of metal. Because they're unequal players. One likes electrons more than the others. Voltaic cells. Concentration cells, on the other hand, are as follows. In concentration cell, the metals are exactly the same. It's the same kind of metal stuck into solutions of the same ions, of its own ions. So that's the big difference. Voltaic, two different metals. Concentration, same metal. Each kind of cell can operate in two kinds of conditions. First one is the standard cell operating at standard conditions, and then the non-standard cell. Standard conditions are as follows: 25 degrees Celsius, 1 atmospheric pressure, and the solutions here have 1 molarity of concentration. One molarity of concentration. In that case, the voltage of the cell is given by this equation. Voltage has a symbol E, so E cell, electrochemical potential, just another fancy name for voltage. At standard, remember our standard symbol is given by the reduction, the standard reduction potential of the reduction half minus the standard reduction potential of the oxidation half. And I'll explain what all of these are in a second. In the case of non-standard voltaic cells, you use what's called Nernst equation, which says E cell, notice I'm not putting the standard symbol, equals E0 cell minus RT over N F ln Q, Nernst equation. Great. On the concentration cell side, remember the metals are the same. The idea is electrons need to see a difference on the two sides to decide what side to move on to, right? The incentive for the electron needs to be, hey, there's actually a difference between this side and the other side. What happens when you have a standard concentration cell? So you have two buckets. The solutions look exactly the same because they're both 1 molar. And it's the same kind of metal stuck in both of them. So the two buckets look identical to each other. So there is no incentive for the electron to move anywhere, right? Because it's two identical buckets. There is no difference. What would you expect the standard potential of the concentration cell to be? What do you think? Zero, exactly. No incentive. There is no difference in the two buckets, so it's exactly 0. So a concentration cell can only operate at non-standard conditions, where the metals are the same. The incentive that the electrons see is that, suppose this is 0.5 molar and this is 0.3 molar. Now you've broken the symmetry. Now you've broken the identicality. Now there's a difference between the two buckets. So concentration cells only operate at non-standard conditions. Okay, cool. And you still use the Nernst equation, but the modified version of Nernst equation, because of, we know what this fact is. Okay, take your general Nernst equation, which is here. And we know that the standard cell potential is 0. So plug in 0 for this guy. So you get E cell equals 0 minus, I can forget about the 0, just minus RT over NF ln Q. This is the modified Nernst equation for the concentration cell. Do you all understand what I did there? Any questions? Okay. That is a high-level summary. Not even high level, it's a comprehensive summary of what's going on. Okay, now let's talk about each of these one by one. How much time do we have? We have enough time. Starting with the standard voltaic cell, which is a very simple equation, reduction minus oxidation. Okay. Question, determine the E0 cell for the following cell. Yeah. Zn, I'm just going to give you a very quick, nice example. Zn plus Cu plus becomes, or let's say 2Cu plus becomes Zn2 plus Cu. Here's a cell. Let's very quickly grab the two halves. So Zn becomes Zn2 plus, and 2Cu plus becomes 2Cu. And just take out the coefficients, because we don't care about the coefficients. Cu plus becomes Cu. Whoops. Yep, all good. My OneNote keeps acting up. I have no idea why. Great. And now you just have to look up a table for their standard reduction potentials. So first of all, the standard reduction potential. So which one's reduction, which one's oxidation? You tell me. Is zinc getting reduced or is copper getting reduced? Right, so this one's going from 0 to +2 charge. This one's going from +1 charge to 0 charge. Yeah, it's the copper that's getting reduced, exactly. So it's going to be the reduction potential of the reduction reaction, which is the copper reaction, minus the reduction potential of the zinc reaction. These values you just copy from a table. There's a standard reduction potentials table with one caveat. The standard reduction table, let me first pull it up to give you a taste. Standard reduction potential table looks like this. You have all sorts of reactions and their corresponding values. But if you look at the half reactions, the standard reduction potential table is always in the reduction format. That's something to keep in mind. It's always in the reduction format. So if you're trying to look for a match for your reduction reaction, which is this guy, you'll find an exact copy. So let's look at it. Cu plus becomes Cu. I haven't put in the electrons, but this should be good enough. Cu plus becomes Cu. Where's my copper? Yes, look down here. Cu plus plus electron becomes Cu, 0.52. Great, so I can just go ahead and copy down its value, 0.52 volts. But for the zinc, you won't find an exact match for zinc becomes Zn2 plus because this is oxidation. You'll find the same reaction, but in the flipped reduction format. So to get an exact copy of your oxidation reaction, you first have to flip it so it becomes the reduction format, and then look it up in the table. So that's Zn2 plus, where's my zinc? Right here. Zn2 plus becomes zinc. See, you see the flipped version of what we need, which is fine. This is negative 0.76. So minus negative 0.76. Cool. 0.52. Double negatives becomes a positive 0.76, and whatever that comes out to. 1.28, I think. Yeah. Okay, let's do another one. Cr2072 minus plus Mn2 plus becomes Cr3 plus Mn3 plus. Ideally, you would want to fully balance out this equation and make it right, but this is good enough for us. This going to this is our first thing, and then Mn2 plus becoming Mn3 plus is our second thing. Clearly, manganese is getting oxidized because the charge is going up, so we'll need to figure out. So first of all, this is oxidation, this is reduction. And let's calculate the E cell. So we should be able to find an exact copy of the reduction reaction. Let's see, Cr2072 minus, where do I see that? Right there, Cr2072 minus, you see it gives you the balanced equation, but we don't care. Cr2072 minus, Cr3 plus on the right-hand side, yep, that's the one, 1.33. Mn2 plus becomes Mn3 plus, that's oxidation, so I'm going to look at the flipped version of it. Mn3 plus becomes Mn2 plus. Mn3 plus. Should be in one of the tables. Maybe I made up a bad example. Mn3 plus 2, Mn2 plus redox potential. Okay, so Mn3 plus 2 Mn2 plus is negative 1.18. Some of these tables don't have all the reactions. That's fine. So negative 1.18. Cool, so that's 1.33 plus 1.18. And there you go. That's your answer in volts. Any questions so far? All right. Now let's take the same equation as above and calculate the E cell at non-standard conditions. So determine the E cell for the reaction below at, let's see, 35 degrees Celsius where hold on one moment. Yes. Where concentration of Cr2O72 minus is 0.5. Concentration of Mn2 plus is 0.1. Concentration of Mn3 plus, say, is 0.4. Concentration of Cr3 plus is 0.2. And the pH of the entire mixture is 4. We'll see where the pH comes in. Don't worry, this is not an equilibrium thing. It's not going to scar you. And the reaction is as follows. This is the unbalanced reaction. CrO72 minus plus Mn2 plus comes Mn3 plus Cr3 plus. This is unbalanced, so the first step is to balance this out. I'm basically giving you the hardest Nernst equation problem that you can expect to find. Okay, this is as bad as it gets. Cool. So first thing is to balance this out. Okay, let's do this quickly. Cr2O72 minus becomes Cr3 plus. Mn2 plus becomes Mn3 plus. This right hand seems very nice. I'm going to start with this guy. I'm going to put an electron there. Electrons are balanced. Manganese is balanced. No need of hydrogen, oxygens. This is good. I'm going to put a 2 there for the chromium. Remember, this is +6 to +3. We did the algebra previously, so there should be a +6 electrons here. 7 water molecules here to balance out the oxygens and 14 H+. Just recalling what we've done earlier. All right, 6 electrons, a single electron here, so times 6. And now this becomes 6 Mn2 plus becomes 6 Mn3 plus 6 electrons combine. Cr2O72 minus plus 6 electrons plus 14H plus gives 2 Cr3 plus 7H2O, and 6 Mn2 plus goes on the left. 6 Mn3 plus goes on the right, and the 6 electrons go here, cancel, cancel. And that's it. That's the clean version. That is the balanced version of the thing. Now, where do we end? Do we do it in acidic medium or basic medium? What can you tell me looking at the question that I've given you? Are we doing this in acidic medium or basic medium? And tell me why.
I think since we have the pH, which is the log of H plus.
Good. Exactly. So that's one reason why the pH is given, because it's acidic medium. Okay, cool. So we'll stop here. Acidic. And now employ the Nernst equation. So E cell equals E0 cell minus RT over NF. I think it is RT over NF. If I'm wrong, it's NF over RT. It's one or the other. LNQ.
Yeah, that's correct.
Okay, thank you. Great. For this reaction, we had calculated the E0 cell previously using the reduction minus oxidation right here. So even if it's a non-standard questions, you want to do the standard thing first because it's part of the Nernst equation. So you want to calculate the reduction minus oxidation no matter what question it is. Cool. So we had calculated this to be 1.33 plus 1.18, which came out to 2.451, I think. Yes, 2.51 volts. Cool. So that goes here. Minus R for the purposes of electrochemistry is going to be 8.31. No, 0.0821. We're not doing energies here. Temperature is the temperature in Kelvin. We have 35 degrees Celsius in the question. So add 273.15 to convert it into Kelvin. That's 308.15. So 0.0821 times 308.15 divided by N is the common number of electrons. Look at what we canceled here. What was the common number of electrons on both sides? When we matched the electrons, it was 6. So N here is 6. F is a constant called Faraday's constant, 96,500 approximately. Ln of Q is our old friend from the equilibrium chapter. Reaction quotient. Remember, products over reactants? Products over reactants and coefficients become powers. Yes, it's coming back. Okay, so it's a fraction. Products go on top, reactants go on the bottom, and only the aqueous ones go in here. This is aqueous. All the ions are always aqueous. We're going to ignore water because it's liquid. Cool. So Cr3 plus to the power of 2 because it has a coefficient of 2. What is my Cr3 plus concentration? 0.2 up here. So it's going to be 0.2 to the power of 2 times water, don't care. Mn3 plus has a concentration of 0.4 to the power of 6. And that's it. For the reactants, Cr2072 minus, concentration is 0.5, coefficient is 1, so just 0.5. What else? Mn2 plus, I've given you is 0.1, coefficient is 6, so to the power of 6. And lastly, concentration of H+. That I have not given you. Who can tell me, based on the given information, what the concentration of H+ should be? You have all the information you need for the concentration of H+. You just need to recall some stuff from acid-base equilibrium.
I think we know the pH is equal to
Yeah,
log of the concentration H+, right?
exactly.
And from there, yeah.
Exactly. So if pH is 4, which means that the negative log of H+ is 4, which means that the log of H+ is -4, which means that H+ is 10 both sides, 10 to the -4. Excellent. So this is going to be 10 to the -4. Oh man. To the power of, what was the coefficient of H+? 14. And there you have it. Yep, that's the one. That's it. Okay. Any questions? I know it's a lot, but it's not complicated at all. Okay. Let's do the last part, the non-standard concentration cell. Suppose you have 2 buckets. Oh, he will put it on the exam. Nernst equation, guaranteed. It is going to be on the exam. I feel so I've scared you by giving you the longest possible question, sort of, in Nernst equation. For example, if this was given on the exam, he will give you this directly. He wouldn't ask you to balance it and apply the Nernst equation, I think. He'd give you this directly. So you just have to do this part, which would make your life easier. So I give you the worst possible case. On the exam, it should be better. Yeah. Okay. Concentration cells. Let's say you have, yes, you have 2 solutions, zinc electrodes on each side, lighting a light bulb. My genius artistry shining brightly here. And the solution contains zinc 2 plus ions. Or they could say that the solution is like zinc sulfate, which contains zinc 2 plus ions and SO4 2 minus. This we don't care. As long as you have zinc 2 plus, among other things, you're fine. But this one is 0.1, and this one is, say, 1. One of them is involved in oxidation, and the other bucket is involved in reduction. Which one's which? Right? So that's the first question. Is the left-hand side involved in oxidation, or is the right-hand side involved in reduction? The idea here is actually very simple. The reaction will try to equalize the two buckets, right? The reaction will move in such a way so that the two buckets are equalized at the end. Now, the zinc electrodes are zinc, solid zinc. There is no difference between the two sides. It's just zinc. The difference is in the solution. So we want to make the solutions the same strength, the same concentration on each side. Now, this side has a lower molarity, 0.1. This side has a higher molarity of 1. So the molarity here should go up. The molarity here should go down so that they can meet somewhere in the middle. That tells you what the reaction is going to be like. If the goal here is to increase the Zn2 plus in the solution, well, where's the Zn2 plus coming from? Zinc converts into Zn2 plus. So that's what's happening here. Zinc is getting converted into Zn2 plus, boosting Zn2 plus concentration so that it can go up. On the right-hand side, you have too much zinc 2 plus in the concentration. We want to get rid of some of the zinc 2 plus. So this is going to happen. The zinc 2 plus is going to get converted into zinc, solid zinc. Okay. Now, which one's oxidation, which one's reduction? Left or right?
Oxidation left.
Oxidation left, exactly. And reduction on the right. Perfect. Because we're going from 0 charge to 2 plus and 2 plus to 0. Excellent. Okay. They can also ask you related questions. For example, which electrode is getting thicker and which electrode is getting thinner as the reaction proceeds? On the left-hand side, you're losing solid zinc because it's getting dissolved into solution. It's turning into ions. Well, that means that this electrode is getting thinner over time because it's getting dissolved in solution. On the other side, zinc is coming out of the solution and getting stuck onto your electrode. So your electrode is becoming thicker over time because there's more and more zinc depositing on this side. So that's a tangential question they can ask. So the side that's getting oxidized is thinning. And the side that's getting reduced is getting thicker, thickening. Another question that they can ask is determine the direction of electron flow. Let's put the electrons on the appropriate sides. So 2 electrons here and 2 electrons here. On the left-hand side, you see electrons are a product. That means electrons are being released. Released into what? So this electron is losing electrons, and those electrons get on the wire and start going through whatever electrical components that they need to go through. This side, electrons are being used up as reactants. So the electrons enter this electrode and get used up in the reaction. So the direction of the electron flow is from the left to the right. Okay, and lastly, let's calculate the using the Nernst equation. The E cell, it's going to be minus RT over NF, ln of Q. Once again, negative 0.0821. Let's say this is also at 35 degrees Celsius, which was what, 308.15 in Kelvin. What's the common number of electrons? 2 and 2. It's 2, 96,500. When it comes to Q, things become a little confusing. They can become a little confusing. So this is the 2 half reactions, right? If I add them up, if I just add them up, they'll look like this. Zn plus Zn2 plus 2 electrons gives Zn2 plus Zn plus 2 electrons. The electrons cancel, but then it looks like this. Zn plus Zn2 plus gives Zn2 plus zinc. Zinc is solid, so that doesn't go into the reaction quotient, but the Zn2 pluses do. This goes on the top, this goes on the bottom. But now the question is, which one's 0.1 and which is 1? That's where color coding can help you. So let's make this green, zinc, and 2 electrons. So zinc becomes zinc 2 plus 2 electrons, and zinc 2 plus 2 electrons. So that goes here, becomes zinc. Let's add these up. So we get the 2 electrons cancel. Let's make that a single equation. And now using this color-coded method, we can see which one's which. So this is the green zinc 2 plus. Green was 0.1. And this is the red zinc 2 plus, which is 1. So products over reactants. So green over red, this is 0.1 Zn2 plus divided by 1 of the red Zn2 plus. No coefficients, so powers are just 1. Okay, so you sort of want to color code or do something like that to keep track of which ion you're talking about, because they're going to be the same ion on each side. This is concentration cell. It's identical tubs. So you want to do that. Okay. That's it. That's the end of electrochemistry. I'll stay for any questions. Otherwise, I'll see you next week for our last chapter. Mm-hmm. You too.
So how do we know that the electron flow is from left to right?
Because the left is producing electrons as a product, which means it's giving out electrons. And the right-hand side, electrons are being used as a reactant, so it's consuming electrons. Push, pull.
Got it. Thank you.
Mm-hmm.
I have a question, Professor.
Yep.
So about you to found that like which concentration should be on the top or like on the bottom. So let's say for example, like someone start with the second equation.
Yeah.
And the other one, it should be the same case.
The normal Nernst equation?
No, I mean just to for the calculation of Q, which concentration should be on the top or which one will be on the bottom?
Oh, it's always products over reactants, the usual.
Yeah, I know, but in this case, you use the first equation, right?
Yes.
The Gn, like which go to Gn2 plus, and the other one, let's say the reduction as the second equation. Now, if we were to use the reduction as the first equation and the oxidation as the second equation to find the total equation, it's gonna end up with the same.
Yes, it's gonna end up to be the same, exactly. Zn plus Zn2 plus becomes Zn2 plus Zn. This is the overall equation. Yes. Are you asking how to distinguish the two Zns?
Yeah, okay. I mean, let's say if we try to reverse this equation, whatever that is in the second on the product, we put it on the reactant, and the one on the reactant, we put it on the product. I think there will be some differences, right?
Not sure I'm following your question.
Okay.
Hold on, let me try to understand.
Okay.
Zn plus Zn2 plus. You know what? Let's do this. So tell me what to write.
Oh, Gn2 plus. Go to Gn. And Gn. go to Gn2 plus.
Correct. This you got by looking at the reduction reaction, correct?
Yes.
And this you got by looking at the oxidation reaction.
Yes.
Okay. You want to add these up now?
Yeah.
Okay. So I'm going to add them up. Maybe instead of color coding, I'm going to mark them as, so this is the reduction Zn2 plus the oxidation Zn gives the reduction Zn and the oxidation Zn2 plus. Yeah.
Yes.
All right. So now it's going to be the oxidation Zn2 plus divided by the reduction Zn2 plus, right?
Yes.
Products over reactants. What's the oxidation Zn2 plus? 0.1.
Okay.
Yep, it will come out to be the same.
Okay. Okay. I see. Oh, the other question, you don't mind going back how the flow of electron should be like it's going like happening from left to right?
Yeah. Oh, because are you asking how I determine the direction?
Yes.
Yeah. Okay. So electrons are being produced as a product means electrons are being given off. So electrons are coming out of this electrode because they're products. They have to go somewhere. Right. So think of the reaction as like happening at the interface of the electrode and the solution. So if products are coming off, they're going to come up. Electrons can only travel through metal. So they're going to come out of the metal that way, products.
Okay.
Here, you want the reaction to happen here, and the electrons are a reactant on this side. And so the electrons are needed and they have to come through metal. So they're coming this way. And that tells you the overall direction. Does that make sense?
Yeah, one last question.
Mhm.
About the problem where you assign the pH. Let's say if the pOH has been given,
Yeah.
which means we should go to the basic solution.
No, it depends. So for example, in the same question, I could have given you pOH to be 210. It's the same question. Right? Because pOH being 10 means that the pH is 4, which still means it's acidic.
Oh, okay. So you mean which means there's no way like for us, to give us like to have like a problem where you have to go to the basic solution to find the basic solution?
You can. Example, pOH being 2. So first of all, our acidity and basicity is in the language of pH, right? So just convert this to pH just to see if the solution is acidic or basic. 12, right?
Mhm.
That's basic solution.
Yes.
Oh, so then you're going to use the basic version of the equation. You're going to add OH on both sides, do this whole business and use this guy.
Okay.
And now for the Q part, one of your products is OH minus. So you're going to use the pOH to get the OH minus concentration.
Yeah.
Yeah.
All right. Thank you so much.
No problem. I thought I had a question. And Alex, we're supposed to swap the anode. Why is that? Swap the anode. Okay. Cathode is where anode is where the oxidation happens. Cathode is where the reduction happens. Is that correct? Yes, okay. You're supposed to flip the anode because remember, the reduction table, the reduction potentials table is in reduction format. So this one is good. You'll find an exact copy of the reaction. This one is not, this one is wrong. You'll need to flip it to get it. Yeah, all goes back to that. Yeah.
Could you explain the directions of electrons again? Sorry, I think I missed it.
Sure. Electrons being produced as a product means electrons are being given off. That much makes sense?
Yeah.
So they have to like exit this area. They have to, they're going away. And the only path that they can take is through the wire, through the metal.
So it would be going to the right, up
Yeah.
and then right.
Yeah, it's gonna come up and then it has to take this turn to follow the wire. And so it's going this
Okay.
way.
Okay, I see.
Exactly.
Thank you.
No problem.
And oh, just so another clarification. So the other one that's where electrons are used, it'd be going from the left down.
Yes.
Okay.
Yeah.
Thank you.
Mhm. Right. Anything else? All right. Oh, I'll see you guys next week.